Okay, just a quick check. Himanshi, can you hear me? Okay, all right. We'll start now. Good morning, everyone. Uh, this is me, Mayank Sharma, with Himansu, and we'll start with the electronics tech loop today. So the session is about tech loop with hands-on electronics part of it. So we'll start now, Himansu. Himansu.
Hello, I hope I'm audible. Yeah. So talking about Techloop. Techloop is an interactive workshop conducted by the students of IEEE-VIT, by the students of IEEE-VIT for the students, which involves hands-on sessions that result in stronger understanding of the concepts to both speakers and audience. So let's talk about one of the major core engineering field, electronics. You see, the fundamental question comes here: why to choose electronics domain? Just have a look around your room. You can find so many electronics devices, from Alexa to even some people have robotic vacuum cleaners. Even electric vehicles nowadays are in light. Every industry is trying to get automated. From the switch in your room to the defense missile, everything is automated and can be controlled over internet. So you see, like there's so many things that can be done through electronics. And here are some of the global companies and their investments made in electronics and robotics for R&D. And in general, average salary package of a robotics engineer lies around 60 to 80K dollars per annum. And like as you can see in the image, Tesla has been heavily investing in EVs and even robots now. About Tata being making one of the biggest EV ecosystems in India. Uh, Talking about Boston Dynamics, they are working on their two of the major robots, Atlas and Spot. So definitely we have a very good market and good opportunity for electronics engineers in future as well. Yeah, Mike, you can.
Okay, so let's start with electronics. And before, as we discussed, where is electronics and what all opportunities are there in electronics for everyone. So let's get started and check what is there in electronics to learn. So we can, yeah, again subdivide the electronics in subdomains, namely embedded electronics, IoT, which is basically Internet of Things, and the last one being robotics. So we'll explain and each one of the subdomain step by step in the further session. Okay, so what do you think this is? Like everyone, I just want a rough guess. What do you think the image on the shown on the screen is? Uh, Anyone? Just give it a try. It may not be correct. It's completely all right. I just want to see if anyone knows what the chip or the photo indicates here is exactly. Okay, I say it's kind of an integrated circuit. Yeah, uh, I got the answer in the comments. Jason said it's a microcontroller. So we'll discuss about later on in the session. So this is an yeah, it is an integrated circuit, which and basically it is a microcontroller of which is of 8-bit, and it has a 8 KB of flash memory, and we'll tell you about microcontrollers uh, right now. Okay, so here we have, starting with embedded electronics, we have two photos here. On the left, we have a microcontroller, and on the right, we have a microprocessor. So the microcontroller is a simple integrated circuit which can perform a particular task at a given time, and it is very useful in many different applications which we'll discuss. And on the right side, we have a microprocessor from a very famous development board called Raspberry Pi. It's a microprocessor is another integrated circuit, but it's more powerful than a microcontroller, and it can run multiple programs at a given time in real time. Okay. All right. So we talked about what microcontrollers are and what microprocessors are. So let's just compare them quickly. So for microcontrollers, it is used in embedded systems directly, and for microprocessors, as we already know, we have heard about Intel and M1 chips, and those come under microprocessors. So they are generally used in computer systems, but and as they are very powerful, we can build multiple complex electronic systems with microprocessor. But with microcontrollers, we just can perform a single particular task at a given time. Microcontroller contains a CPU, RAM, and ROM all integrated in a single package. But microprocessors only have a CPU, and they had to be integrated with RAM separately. In microcontrollers, all the components are internally connected, but microprocessor is a separate unit, and we have to connect the ROM and RAM and different parts externally to the microprocessor. Microcontrollers consume less power because they have a very limited amount of resources, and microprocessors are powerful and they provide high computational power. So they take a relatively higher amount of power, but the processing time is slow. So that's there. Moving on.
Yeah. So let's talk about applications of embedded systems. So here are various fields where you can see where application of embedded system is there. So from industrial robots, in case of industrial robots, to control the particular movement, to control the particular action, to receive signals from the modules, like from transmitter to receive the signals. In those case, we need embedded sensors. GPS receivers are there. There comes GSM module which you can use to call. In that case also we can use this. Then digital cameras, DVD players, all of these things, set top boxes, everything that you can see consists of an embedded system. So which is used in every of them. So like from gaming, consumer electronics, industrial equipments, cars, everywhere we use embedded systems. So how to get started with the embedded systems? So Arduino and Raspberry Pi are one of the best and generic development boards to get started with. And development boards are just PCB designed in such a user-friendly manner that beginners can use them without doing any kind of soldering. So also you can make projects from basic level to an high level using these development boards. Yeah. So Arduino is the best way to start your journey to explore embedded systems. And let's have some more detailed about Arduino.
So as Shivanshu discussed about what an Arduino, like about an Arduino. So the first question arises is what is an Arduino? So Arduino is just a completely completed circuit board with a microcontroller inside it. So to use a microcontroller, we need a lot of components with it combined together. So to perform and program it, but what Arduino did is they provided a development board combined all together so that anyone can use it's beginner friendly and anyone can use directly without having to get all those components together and use the microcontroller. So it's very beginner friendly and it is also programmable. So that's what Arduino offers. Then we have let's talk about the advantages of Arduino. As we talked already, uh, already, it is easy to use and it has a very huge community support. You can just hit out any project on the Google and you will find at least one project related to your application. It also has a very good documentation explaining what the function does, input, output, and the application with an example. And there are a lot of developers on the internet. You can always find someone on the other helping each other to build an Arduino project and to provide the help in every aspect, be it programming or the hardware part, even debugging. So those are the advantages of using an Arduino. So moving on, let's just see few of the projects in Arduino made using Arduino.
Yeah. So these are some of the projects that we have. So the first one is a self-balancing platform. So this is a two-wheel drive. This is a bot, and it's made using Arduino only, and it has multiple sensors and motors to balance it properly. So the project works as in, like, when you give some external force, then it reads as per the gyroscope readings. It adjusts the motor and makes it balanced. So like it won't fall even if you apply some force to it. So this is really good project. So it uses accelerometer and gyroscope, and a microcontroller is used to implement the logic, and the motors and drivers are to adjust the torque or to counter the torque. The next project we have is a Biorotor Drone. So this is one of the complex projects that you can think of using an embedded system. It's not just embedded system; it includes robotics as well. So it has multiple degrees of freedom, as you can see in the image also. Like it is very smooth while interacting within the room as well. So it is safe to use, and like it's a combination of embedded system, electronics, and like robotics as well. Yeah, man, you can go.
Okay, so also since we saw those two projects, we have more projects lined up here. So the first one on the left is a spider-like wireless robot. It looks complicated, but it's made using a microcontroller itself because it just has servo motors, which are basically motors which can be controlled at a very precise angle. And if to power it up, there's a microcontroller in the heart of it, which is programmed to control, and the commands are sent via mobile application remotely to the. So it looks like a spider, but it's just a simple robot using motors and a microcontroller. And on the right side, we have a gesture controlled four-wheel drive. Basically, it's just a robo car with four wheels, and we can control it using the gestures from our hands or general gestures as programmed in the microcontroller. So we use a component in here which is an accelerometer. We just calculate accelerations in x, y, and z direction, and accordingly detect a gesture and allocate that gesture to a particular action in a four-wheel drive. So that's what it is doing on the right side of the project, like the project's one on the right side. So since we have already discussed about and seen a few projects in Arduino, let's get started and make a simple project of our own to get started. Okay, so to start, you do not need an hardware exactly to perform the task with us right now. You just need to be you just need Tinkercad. Just Google it up. There's a tool called Tinkercad, and quickly log in if you have an account already, or sign up, and I'll tell you the brief after that. Just tell me in the comment section if you have already logged in. Okay, I see people have logged in already. So hope you can see my screen. So this is after you log into Tinkercad, you'll head on to this page. Make sure you have selected the circuits part on the left side of the panel, and then click on Create New Circuit. It will take you to the new sample circuit screen. The internet is a little bit slow. Just give me a minute. It will be there. For the time it's loading, is everyone logged into the Tinkercad server now? Unmute the mic.
You guys can ask.
You all can ask doubts in the comment section. Meanwhile, the screen is loading. Internet is a bit slow here. Okay, here we have the screen. All right. So let's get started and first click on the component like an Arduino and just drag and click again on the screen, and the Arduino will be there on the screen right in front of you. So for the hands-on, let's just like try to implement the very basic features like reading and writing analog and digital values. So for that, we will have an Arduino right in the center. Uh, then we'll have an LDR. LDR is basically a light dependent register, which is also called a photo register, as we found in the right side of it. It's in the basic components. Just drag and drop and click on the screen to pin it. Then we'll use a LED. We have an LED here, and we'll have, and the third component we will have here is an IR sensor. Just search for it. You'll get an IR sensor from the components tab itself. Here it is in the, so I got this. After this, we just have to connect the cathode to the ground of Arduino, and we also need two more resistors just in just to manage the current, because if we connect directly 5 volts directly to an LED, it might blow off, because most of the LEDs are powered generally by 3.3 volts. So that's why we need a resistor in parallel with it, and just connect the register with the LED, and let's select one of the digital pins on Arduino. Digital pins of Arduino are just pins which can be turned on and off, which is because, and it's called digital because it just had logic levels which is high or low. And the on the pins where we see a analog like sign in front of the pin, those are called analog, like PWM pins, because they can output variable voltage using using a concept called pulse width modulation, which is basically changing the frequency and turning on and off the digital signal constantly at a particular frequency, and for a particular time it is turned on, and for a particular time it is turned off. So if we control the ratio, we can control the output voltage. So we just chose pin 10 for now for LED, and let's just connect the IR2. So for power, we need VCC, which is basically 5 volts. And for ground, let's just connect it to the ground of Arduino. It is connected, and sorry, I made a mistake here. For the ground, we'll connect ground to the ground pin. And for the output of the IR sensor, we'll connect it to a digital pin. Let's just say pin 7 for now. And LDR, for LDR2, we need a resistor because the LDR resistance changes with light intensity. So if the resistance goes zero, it is not good for an electrical circuit because it will be short circuited. So we'll connect it to the ground. Okay, it is connected right now to ground, and the other terminal to a power source, which is 5 volts for us. After this, we need an analog voltage input, which is for getting an analog input, we have an ADC, which is analog to digital converter in Arduino. So the pins provided for those are on the bottom right corner, which are A0 to A5. So first, let's just start with A0 right now, and we'll connect A0 to to one pin of LDR. Okay, so this is basically the circuit is completed. We can add a buzzer here. Okay, and to get the buzzer, just type buzzer in this, and we'll get a piezo buzzer inside from the panel itself. When the negative of the buzzer will go to the ground, and the positive will go to one of the digital pins of Arduino. Let's just say 11 for now. So this completes the circuit. Now we can get started with the code. So the code here is written in C++. Although it looks a bit scary for the first time, but it isn't. Just trust me. Uh, First, we need to define the pins we are going to use, which is basically of an integer type. So we have an LED. An LED is connected to the 10th pin here in the Arduino. Then we have an IR sensor. IR sensor is connected to the 7th pin, and similarly, we'll just write down all the pin numbers and make a variable for it. We have the buzzer, and buzzer here is connected to the 11th pin here. Then just give me a second. Then we have our LDR finally, and we have connected the LDR to A0, which is analog pin. So we have all the pins ready here, and we have to set a pin mode, which basically just pulls up or down the built-in registers so that the initial voltage is not floating. It's either high or on for the input. So if we have a digital input, we just have to set the mode for it. So for this, we have an LED. So for LED, we are using an analog voltage output. So we don't need to for the digital pins, which is basically buzzer. We'll set the buzzer to an output pin. It's define it as output. To get the debugging messages, we need a serial. Serial basically to communicate through Arduino and your computer and get the messages printed on a screen. So and with a baud rate and a default baud rate, which is basically a speed of communication with the Arduino, which is 9600 here. So we just initiate serial here in the code. We have this defined, and let's just in this we have a setup and a loop inside Arduino. Setup once the Arduino boots up for the first time, setup is run, and then we have a loop function which just keeps on running the entire time Arduino is powered on. So now we'll you make use of the different values we get from the sensors we used here. So for LDR, let's just get the value for an LDR value. And to get a value, as we have already talked, we are going for an analog value because it's going to change. The voltage is going to change with time, with the light intensity. So to get an analog value of voltage, we have a function called analog read, and we just have to provide the pin number of the LDR. So here it is. So it will get us the value from 0 to 1024 because Arduino has a 10-bit ADC, which is analog to digital converter, and 10-bit ADC value ranges from 0 to 1023 because we can have 1024 values between with a 10-bit ADC. So then we have a buzzer. We'll get a value from LDR and we will get a value from IR sensor. So let's get the IR value as well. To get the IR value, we have to read it digitally. So as goes the name, and we have a function similar to that called digital read on the IR sensor pin. So we just provided a parameter. We'll get the value of as 0 or 1 because if an obstacle is there, it will give a 0 as the output. Otherwise, it will give 1 as an output. So now we have it. Let's just print the values. To print the values, we can write serial.println and let's just print the LDR value for now. We have written the code here and click on start simulation. It will start the simulation right away and you can see the output on the serial monitor. Click on the LDR and you can see the intensity. You can control the intensity level on the top of LDR using the simulation. See, as I change the light intensity, and as I increase the light intensity, the the resistance and the output voltage values changes. And we can see on the screen serial monitor as well the value is changing. Similar for an IR value, we can see the IR value change as well. You just need another one more component for it, which is an IR remote to send IR infrared waves to the IR sensor. And just we have the remote here, and we'll run the code again. So we have one right now because there's no infrared source in front of the IR right now. And if I press a button, you can see flashes of 0 on whenever I press the button, the 0 is printed on the console. So that's how the IR sensor works. So here we have it. And since we have already tried this, let's just try to turn on the buzzer. To turn a voltage on at a particular pin, we have a function called digital write. We just have to write digital write and pass the pin number of the buzzer, which is stored in a buzzer variable right now, and set it to high. High basically means high voltage. And run the simulation again, we should get the buzzer turned on after the simulation starts. So you can see on the simulation there's a visual which says that buzzer is on right now. You can hear the sound in the computer if you're trying with it. Then similarly, we just to turn off the buzzer, we just have to set it low, and this covers the buzzer, LDR, and the IR sensor, and we are just left with the LED. So let's just control the LED brightness and using the code. So to control the LED brightness, we need an analog voltage, which is basically a changing voltage on an LED for the LED. So we have an LED pin, and the output voltage ranges from 0 to 5, and the different value. We have an 8-bit digital to analog converter, which offers 256 different values. So it ranges from 0 to 255. So if we give 255 as an analog sorry, it should be analog, right? So if we do it like this, it should turn on the LED. So the LED turned on. So and if I change the value to, let's say, half 127 and start the simulation, it will reduce the LED brightness. It is lower than what it was before. So this was for the hands-on demo for electronic for Arduino, where we covered analog read, analog write, digital read, and digital write using 4 different kinds of things: uh, an IR sensor, an LDR, an LED, and a buzzer. So this was for the hands-on. So and we'll start go back to the PPT now.
If you all have any doubts, you guys can ask.
If anyone has any doubts, just put it in the comment section. We'll clear it as soon as possible.
I hope you all can see the screen. Yeah. So before moving on ahead, we have a small demo of MPU chip as well. So earlier we saw this project, right, of two-wheel drive, which is self-balancing car. So it uses a gyroscope, right, gyroscope and accelerometer. So we have a demo for that as well. I'll just reshare the screen. Give me a minute. I'll share. One second. I hope my screen is visible. Uh, can someone just confirm in chat box, please? Mike, is my screen visible? Can someone just confirm?
Y- y- Yes, it is visible for me as well. Someone comment. Yeah, it's visible for
Yeah.
me.
Okay. So this is the code that we'll be using to run the gyroscope. So there's a predefined library to use this gyroscope called as MPU6050. And so here we'll be starting the serial monitor to get the data on the data directly from the Arduino. Then we'll initialize the sensor. We'll wait for sensor to send the values. So this is how it like we'll put an if loop. So we'll wait for sensor to send values. Then we'll be setting the range of the sensors. so that like the range in which we want the values to be printed. So there are multiple ranges available from which we can choose whichever we want. Then we'll set the range for gyroscope as well. Here, gyroscope range, there are multiple ranges for that as well, so we can set that. We can set the filter bandwidth as well. So it's not necessary to do, it's optional, you can do or you can skip that. Yeah. Then in the loop, we'll be getting creating events every time. So like we'll be getting values of acceleration and gyroscope readings every time, and we'll be re getting like getting the values in real time. So I have the board connected with me. I hope you guys can see the screen, like see the video. Like I'm having the sensor here. This is the MPU chip connected to an Arduino. So what I'll do is I'll just change the orientation of this board, and you can see the changes. So like if I change it like this, I can see there's a difference in the Y reading, as you all can see. So the Y-axis reading is changing for acceleration as well and for orientation. So if you want to see the change in Z, so like here we can see there's a change in acceleration in Z value. So this sensor can detect temperature as well. So the readings are quite unstable sometimes, but it's generally used for gyroscope and accelerometer purpose only. So this sensor, like this is how it gets the reading. So like if some external force unbalances it like this, so it gets the reading, and as per that it unbalances it. And as per that, the motors, like by using the Arduino, it will run the logic, and as per that the motors will adjust and the platform will be balanced. So that's how this MPU chip, which is a gyroscope, works. So that's all for this MPU demo. We'll move ahead with the slides once again.
Hope everyone was able to follow the hands-on, got an idea about how to use Arduino if you haven't started before.
I hope you guys can see my screen. Can someone just confirm in the chat box, please?
Okay, we have some doubts in comment section. So Aditya, can we use an MPU to make a compass? Yeah, we can definitely. To making compass is not exactly done by MPU 6050. Like there's a there are two kinds of chip, MPU 6050 and MPU 9250. So the one we sold doesn't have a magnetometer in it. Magnetometer basically uh, measures the magnetic field intensity, and if we set a threshold by calibrating manually, we can get in direction. But the one we showed you right now doesn't have a magnetometer. So if you get the MPU 92501, you can get you can make it use it to make a compass as well. Uh, we have another question. Himanshu, will you take it?
I'm sorry, I'm muted. So, Nishchay is asking what exactly is baud rate. So, baud rate is the rate at which your computer speaks or sends data to the hardware. So, see, there's a serial communication between your hard Arduino and the your computer. So, this communication can be achieved or can be done at multiple speeds. So it's possible that we can have multiple baud rates like 9600, 115, 200. There are multiple baud rates available. So as per the microcontroller that you have in your system, in your embedded system, so as per the hardware specifications, so you can choose different baud rates, but we have to make sure that the baud rate on both the sides, as in what we are using, what we are sending to the hardware, like from the code, and what we are using to view the data that we receive from the hardware, like on the serial monitor. Both the baud rates should be same. Then only we'll get the data properly. So if it's not if it's not same, it will send some garbage values. So that's how baud rate works, and like that's. I hope this answers your question, Nishchay.
All right. So we'll move next. Okay, so we are done the Arduino hands-on and basics on what Arduino is, how it works, what are the advantages, and also had an hands-on on what to make it and to get used to the basic functions of an Arduino. Yeah, and also we got an LED blinking, right? Like a pause there, as the meme says. And hope you'll become an expert in Arduino and learn something from this tech loop about an Arduino. So we'll move on to the next part of it, which was microprocessors and development board related to microprocessor. And one of the most famous microprocessor based board in the market right now is a Raspberry Pi. So we'll tell about you right now.
Yeah. So talking about Raspberry Pi. So it is one of the advanced development boards compared to Arduino. So it's 40 times faster than Arduino. You can collect many more sensors as compared to Arduino. So question comes to mind, like why we need Raspberry Pi? It's like Arduino is doing the work, so why you need that? So the major concern being the computation power, the memory, the RAM that Arduino has is quite less as compared to Raspberry Pi. So if I want to control 15 or 20 motors at the same time, the Arduino can't do that. So in such cases, it's preferable to use Raspberry Pi, and it's not just like it's the only thing that you can do on Raspberry Pi. You can literally build a proper computer using Raspberry Pi. You can play games on that. You can host servers. You can host websites. You can even play Minecraft as well. It's like a computer, fully furnished computer, and this is what a Raspberry Pi looks like. So there are it's like it has micro HDMI ports. You can connect an external desktop as well. So it has a Wi-Fi chip inbuilt in itself. You can connect external sensors. You have 40 GPIO pins, so you can connect multiple sensors to it. And here are some of the simple projects that are made using RPi. So as we have seen in the embedded projects, like this one is this one is using RPi. So in this, what we are doing is we are using computer vision to detect the face of a person visiting your house, and it will be shown directly on the camera as well. And it can detect whose face is that, and as per the detection, it can open the door. Like if you wanna if a particular face is there, then only it will allow you to then only it will allow you to enter the home. So this is one of the cool projects that's made using Raspberry Pi. Yeah. So another project that we have is this is a lighting system made at home. So as you can see here, we are connecting, like we are controlling so many things, like all the Christmas lights, everything is there. So in such cases, using an Arduino would not be a good option, because it can't handle such number of computations. So that's why it's better, like as you can see, there are so many relays in this. So there are RGB lights, everything is controlled. So it's better to have a Raspberry Pi controlling this all this. Yeah. So as the projects we saw earlier, all of them, literally all of them, were working without any internet, right? So just imagine the scenario when we connect the internet to it. So let's talk about IoT. So in IoT, we connect things through network embedded with sensors, softwares, and other technologies for the purpose of exchanging data over devices of the all of the devices over internet. So it's like you can control anything from anywhere, like from any part of the world. Just the thing you need is connectivity to internet. And it's not just about controlling, it's about automating. You can automate things using IoT. You can even upload the data to cloud. So for example, if there's some place I want some data, for example, let's say temperature, humidity readings, so I can just put up a sensor and it will just directly send the data to my cloud. So having the data with me, I can use that data for some processing, any type of processing that I want to do. We can do it there. So that's how IoT works. So a simplest project that you guys can think of is a home automation. Like we all must have dreamed of having a button directly next with us, and let's just press it on your mobile and lights switch on and off. So this is one of the simple projects. It uses four relays connected to a node MCU, a development board, which we'll be talking about ahead. So this project can be used to switch on the lights and fans directly just by clicking on your phone. So this can be one of the good projects to start on with.
Okay, so here we have another IoT project. We have a very small, like it's you can see on the screen, right? It's a relatively very small device, but it's connected to the internet at all times, and you can control home or like any remote device using which is connected to the internet using this switch. And this switch is powered by a very small battery. It's a very tiny battery and it consumes very less power, but it can be connected to the internet, and it also has a microcontroller inside of it, so you can program the logic and control any remote device with it. This is one of the great projects in IoT.
Yeah. So to get started with IoT, Node MCU is the best option. It's an Arduino development board which has a Wi-Fi chip on it, so you can just directly connect it with your internet and use. There's an add-on for Arduino IDE as well, so you can directly use the Node MCU with the same code in the Arduino IDE only. So you just have to make some changes in the code. So it's very user friendly. It has a very good documentation and has multiple communication protocols which you can use, which are not just over internet. There are some which work without internet as well. So that's also another advantage. So it has digital input output pins. It's small, it's efficient, it's really good to use. Uh, then yeah, so that's how after connecting it, we can have various, we can do multiple things. And
Okay, so we talked about what a node MCU is and what IoT is, development board such as a node MCU. So why not try one? I'll explain you just quickly. We'll use a node MCU and connect it to the internet as a remote database, which is provided by a organization called ThinkSpeak, and we can send data over there through the internet. This is of how IoT works. So I'll share my screen right now, and just give me a minute. This seems a problem. Just
Give us 2 minutes. Just there is an internet issue. Give us 2 minutes. Just there is an internet issue.
Hi. Hi, yes, yes. Hi. Okay, so sorry for the delay. We'll start with the IoT hands-on now. So here we have the code, like similar to the code we had for Arduino hands-on. Here we for Node MCU, it's okay. Can you all see the screen right now? Can someone compare, like confirm right now if you are able to see Arduino screen? Okay, just give us a minute. Okay, hope you all able to see the screen now. Can someone confirm? Okay, okay. Okay. So, okay. We for Node, it's Node MCU. We can program a Node MCU with the Arduino IDE itself because there are boards available for like it's Arduino IDE supports Node MCU board as well. You just need to go to boards manager and add the entire ESP8266 library boards and you can use it right away. So right now I have this Node MCU board selected and I have Node MCU connected at a port called this and we have the code here. It's similar to what we did in Arduino hands-on, right? So firstly, we have two libraries here. Since we are going to send data to ThingSpeak, we have a Wi-Fi library which is defined for the Node MCU, which is Node MCU is basically powered by ESP8266 module, which is a Wi-Fi based module. with a microcontroller, and then we are going to use the library for ThingSpeak, which ThingSpeak already provides. Then we need a Wi-Fi SSID, which is basically the name of the Wi-Fi, and then we need to provide the password so that our node MCU can log into it. We have a Wi-Fi client class all defined already in the library. So we create an object of it with writing Wi-Fi client. We need a channel number. A channel number is basically the. I'll tell you about this by sharing the by sharing with you ThingSpeak how to get like set up the ThingSpeak website. Then we also have an API key to send data. We to for the authorization. Then we have a rather than using a delay function in Arduino is basically used to delay the entire program by a few milliseconds. Whatever we write in the number is in milliseconds, and we are not using milliseconds here. Rather than we are comparing the last time and the current time, and if it is more than a particular time period, we just go again with it. So we define last time and timer delay for the delay we are using right now is of 20 seconds because it's 20,000 milliseconds right now. And the default baud rate for Node MCU is 115200, and we are using a station mode, which means the Node MCU will get connected to the Wi-Fi as a device and not as a hotspot. Then we'll start the ThingSpeak client by writing ThingSpeak.begin function. Then we come inside a loop. We compare the current time minus the last time, and if it is more than 20 seconds, which is basically 20,000, we start with the processing part. So if we are not connected to the Wi-Fi, which this line means exactly, if we are not connected, we try to connect to the Wi-Fi and we begin the Wi-Fi for the particular SSID and password and wait for 5 seconds to get it connected. And if it is connected, it will move out to the next part. Then right now we are sending a random number between 1 to 10, which can be written using random here, and we'll get the data, and we can send the data using thingspeak.write field. First one is the channel number, which I'll tell you soon, and then we have one which is field number. Like inside channels we have fields. So one here means the first field in the channel. Then we have our data, which is basically a random number between 1 to 10, and we already defined the write API key. So after executing this function, it will return a response code as we saw in we see in web requests. So if the response is 200, it means the channel was successfully updated, and otherwise there's some problem, and it will be printed on the screen right away. Then we allocate. Then we say last time is equals to current time, and this is how it is. Now it just keeps repeating on, and it sends data every 20 seconds. So this is how it should work. Uh, okay, so now I'll show you how to set up the ThingSpeak website. Can you all see my Chrome tab? Okay, I hope you are able to see the tab. So to set up ThingSpeak, which is basically where we send our data to the cloud, just head on to thingspeak.com and you'll have to log in there with your ID and password if you already have an account, or create a new account. And after creating a new account, you just have to go to channels and my channel. This will take you to the channels page. So currently I do not have any channel in my account right now here. So I'll create a new channel and give it a name. Let's for now just say Techloop. and we have a field label one. So field one is just say my data, and this is what this is a channel named Techloop, and we have the first field as my data. So we have a channel, and there can be multiple fields in a channel. So let's just leave the other parts for now and start save the channel. So it will just create a new channel right away. So now I have a channel named Techloop with with a field called my data, and it just keeps now this thing is active right now. So we need an API key. So the API key I already mentioned, you can find it in the API keys tab. We just have to copy this code. We are going to write data, so we need to copy the write API key, and I paste it in the uh, Arduino code right away there. So I already did that while showing you the code, and there was a channel number. So I just had to get the API key. I got the API key. Now I'll flash the node MCU with the code, and we should be good to go. Okay, I'll show you now. Okay, so we have our ThingSpeak set up already, and it's ready right now. And I've written the API key here with my with my hotspot name and password. I'll flash it to the node MCU now. So the sketch is being compiled right now. I've selected the port. Make sure you select the port. We have a node MCU selected as the board. After the code is compiled, it will be uploaded to the board. It takes a bit of time. Just a minute. Just give me a minute. It will be done. So okay, the code is compiled now and it is being uploaded. Now the code is updated successfully. We just need to switch the baud rate to 115200 as we defined, and wait for the output. So as you saw, there was a line it was attempting to connect. It's trying to connect to my hotspot. Just give it a minute. The output will come right away now. It's trying to connect again. So we have the output again. I resetted the board. Now it's starting again. It's trying to connect. So it's connected now, and we'll have to wait for 20 seconds. So we have the first thing is done. We have it sent the data to the channel successfully, and we have the log here in the serial monitor itself, and we can see the data updated on the sheet on the ThinkSleep website as well. We got a random data of value 6 in here. and after 20 more seconds we should get another data and it should log. Okay, it logged here. So we have another successful data sent to the ThinkSpeak website backend, and it will reflect here in a second. Yeah, so again we have another data. We got 6 and 6 within 20 seconds, and it is being sent to the remote location through the internet. So this was a demo for IoT. Hope you understood whatever I told you right now. If you have any doubt, you can just ask me right now. You can put your doubts in the comment section.
Okay,
Okay,
so
so
that
that's
was
it
it for IoT.
IoT.
Now
Now
we'll
we'll
move
move
on
on
to the
to the
robotics
robotics
part.
part. And March.
Yeah. So let's talk about robotics. So the fundamental question is why robots we need? So to automate things, to as because we engineers are lazy. So like, but there are more solid reasons and than that as well. So let it be working for hours or say getting highly precise results in any task. They can do everything for you. So it's like it makes our lives easier, good working speed and efficiency, like more accurate results. Uh, yeah. See, so let's have a demo of some of the great advanced robots that we have. Yeah. So this is Atlas, one of the robots made by Boston Dynamics. So as you can see, the movement is quite smooth. The way it moves, the way it interacts. This is one of the best robots in the world that we have currently, and like you can see by the video itself. Yeah. So the way these robots works is really cool. So the thing is they have multiple sensors and actuators which let them know what they have to do next, what environment is around them, how they should interact for a particular environmental factor. So that's how they work. So yeah, that's we have. The next robot that we have is Spot. This is also a robot made by Boston Dynamics. So yeah. So this also consists of multiple sensors, cameras, and it can send data over internet. It can be used in various places where humans can't go. So in case of like high temperature regions in various places in industries where the humans can't reach, there you can use that. You can use it as a collecting data as well. So like every day if you have to connect, if you have to get the data every day every time, so you can use the Spot as well. So these are some of the cool robots that we have seen till now. So after watching all of these videos, you must be thinking this, right? You need lots of bucks to make a robot. Like the quadruped Spot that we saw is sold for $75K. So imagine the overall project budget considering research, then trials and all. So, but you don't want money to, like, you don't need money to learn robotics. It's free. So this is where ROS comes into picture. So ROS, the full form being Robot Operating System, is an open source robotics middleware. So it's not a operating system, but it's a framework which is used by robotic enthusiasts and engineers to design robots without actually having an hardware. So imagine someone who works on the software thing, like can't like he doesn't need to buy hardware to test his robot or like the test his software. So it's very easy. You can just make a simulation in ROS. You can use that simulation. You can run multiple scripts and use this. So the simulation you're seeing on the screen, This is also made using ROS only. Yeah. So this is how ROS works. Like you can do multiple things. You can do literally anything that you want. You can run Python scripts. You can have multiple things working at the same time using ROS. So uh, yeah. So this is how ROS interface looks like. So as I said earlier, you can run multiple scripts at the same time, which is not possible in Arduino or Node MCU. So that's the plus point that we have here. So and like keyboard controls are available. You can use joysticks as well. So Python C++ is used here. So it's really good. So next thing we have is advantages of ROS. So it has packages for everything, literally everything. You can it's language agnostic as well. You can communicate between a Python node and C++ node as well. So that's another advantage. It has great simulation tools. The simulation tools in ROS are really good. You can even add physical parameters. For example, wind is there in particular direction. If you want, you can add gravity also. So if you want to test a drone simulation, you can add the gravity properly. You can test, so the like it's like if it works in the simulation, it will work in the real life as well. So simulation tools are really good. Then you can have multiple robots that can work at the same time. Then you can write everything from scratch for any type of work you are doing. For example, if it's software work or if it's a hardware work, you can directly use those packages as well. Yeah. So this is how a ROS simulation looks like. So this is one is of a Prius car. So it's a simulation car made in ROS only. So this is how the simulation window looks in case of ROS. Yeah. So this is the car. This will be like a self-driving car, and we'll be showing you the Arvis part of it. Like yeah, so this is the perception part. So like the one which we saw earlier was how we see the world, and this is how the bot or the computer will see its environment. So see this, it has multiple accesses for each of the components of the car. Then it has multiple sensors to actuate and to get to know what or different things are there in front of it, or like what's in there in the environment. So this is how it works. So this is where embedded also comes into picture. So like you have embedded sensors which are connecting with the computer with using ROS. Yeah. So let's try out Turtlebot 3. This is one of the simulations in ROS. Just give me a minute. I'll reshare the screen. Can someone please confirm if my screen is visible? My- Is it visible? Yeah. Okay. So this is how you have to run the ROS on Ubuntu itself. So what? Yeah. So this is where we have our robot. This is Turtlebot 3, one of the robots. Yeah. So this is how the robot looks. And as I said earlier, like you can run multiple scripts as well. So I'll just add another script and show you like how it works. So like there are these commands which are already written. So like you can use those commands and get the data. Yeah. So as I earlier showed you, like how robot perceives any of the environment. So this is how it looks. So you can see here. So like this is the side robots facing, and like these are the walls where the robot can see embedded comes in picture. Like how it senses, like what type of sensor it uses, so what type of data we get. So as per the data it processes and makes this map. So I'll run another script as well to move this. So like as you can see, like I'm having three different scripts running at the same time, and I'll show how. Yeah. So as you can see, as the bot moves, uh, so this is in real time, as like as we see the environment, and on this RViz, this is where we see how robot perceives, and like it makes a map. So like the this map will be saved, and the bot can use this map to detect where there is an obstacle or not. So this is how we can make multiple things, and like we can use this case like the robotic vacuum cleaners that you have nowadays. So like if you bought, you have to first scan your room. So this is what the process is. So like that's why we need to scan the room, so that we know where an obstacle is or where it is not. So this is one of the great simulations that Ross has. So you can scan the whole room, you can save the maps, and like as we save these maps, we can use the Python scripts, and we'll run those Python script to navigate from one point to another. So we can write Python scripts for that as well. This is That's all for the robotics demo. I'll shift to the slides once again. Give me a second. I hope my screen is visible now.
Okay, so we talked about robotics in general, then figure out why we need ROS and what ROS offers to us. Then we saw a simulation on TurtleBot 3. And for the fact, TurtleBot 3 and TurtleSim are two different things. So that's just keep that in mind. And am I audible?
Yeah. So let's move on. Next thing we have is what we have made at IEEE.
So let's just see if the projects we have, our recent projects that we have made in IEEE for in electronics and robotics. So starting with the first one, this is a two-wheel drive, but it's not just a normal two-wheel drive. It is a two-wheel drive that is being controlled using robot operating system, as we discussed, wirelessly through the Wi-Fi network, and we are controlling it using Python scripts, and it can be controlled wirelessly. We have used Arduino Node MCU talking to each other via serial communication, and the Node MCU talking to the ROS interface using TCP wirelessly. So this is one of the uh, robotics uh, robotics based project that we have made in IEEE. Then moving on to the next one. The next one is lead bus. This is another good project that we made because and in this project it when you look at the project, it just looks like 8 LEDs and a node MCU. It's just that simple, but it is not. Believe me, it is not. Uh, so what we did is we just fixed it to a fan rather than making it move using a normal motor. We fixed it on a fan altogether. Powered the node MCU with a battery and a logic. Node MCU connects to the internet, and when the fan rotates, we precisely turn on the LEDs at the exact amount of time, and we can get an entire schedule. Like the main purpose of LED bus is to show your schedule right on your ceiling fan. So if you turn on a fan at your full speed, and it will fetch data from Firebase, which is the backend which is a backend framework offered by Google. It takes data from there and shows your entire schedule on the fan itself. So this was one of the projects that we made. Let's see a demo video of how it looks when it is running in real life.
Yeah. Okay. So this is how the LED bus project was. So like as you can see in the screen, like this thing is actually set up on a ceiling fan. So this is how it looks, and you can literally send any data that you want, any timetable that you want on this. Yeah. And this one's another project, embedded project that we made. Like it's a automated drive car, just a two-wheel drive car. It's automated by itself, so like it will sense an obstacle in front of it, and it will move accordingly, and it runs flawlessly as well. Like as per the ending this session, and like if you have any doubts, put it up in the chat box, and we'll be providing you the well documented resources page for you to start with electronics as well. And if you have any doubts, you can join our IEEE-VIT's Discord tech server. You can get contact for any of us, and you can get clear your doubts.
Thank you everyone for attending the session. Hope you enjoyed it.
Yeah, or if you guys have any doubts, you can ask.